And now, you know, there have been all these children's, some of them that are accidents and everything else. You know, I realize I'm in no way related to Fano. My experiences was that I was one of the chemists at Chicago who was tolerated by Fano. That I would go down and I would talk to Fano, and we would talk, and sometimes it would last a half hour, sometimes it would last an hour. And he'd usually end up being, toward the end, he'd say, I think that's about enough for today. Now, you know, I knew it wasn't a bad situation because there were those chemists who, after they saw Fano once or twice, that was it. So at least I fell into the class that was not thrown away. I never could figure out exactly where I was, and you know, it was quite clear that Fano, you know, had let's say a sense of understatement when he described people. And you know, so this went on when I was a graduate student. Then I went off and did a couple postdocs, and then I spent 5 years basically as a research faculty at Chicago, in which I spent a lot of my time at NIST. And this is where I really began to learn MQDT from people like Fred Meese and everything else. But I'd still come back, and I would be there, and I'd run into Fano, and we'd talk about code collisions and things. And you know, again, same old kind of style. And sometimes it would end up with, I think that's about enough for today. But I did one time get a compliment from Fano. And the compliment was, I just come back from here having probably the previous time said something to him about code collisions or something. And I am sure after I left, he spent 15 minutes doing what I had done in 6 weeks or 3 months. And had finally realized that, you know, this was really kind of interesting. Because when I came back in, I walked in, and there was Ugo. And Ugo says, you know, these code collisions are kind of interesting. So, what did I learn from all my conversations with Fano? I mean, with Fano, it was like he was always on the inside, and he was always, what is important? What is the essence of the issue at this point? And the tools I actually learned from other people, but of course, I'm aware that Fano is the one who actually contributed those tools to us. So let's talk a little bit about MQDT for a moment. What I've showed here is basically, you can say something like a Lufano plot, but basically, you know, the first thing you learn in code collisions is there are two independent parameters for any alkali atoms. There's a singlet potential and there's a triplet potential, and there's exchange coupling between them. So there's a phase of the singlet potential and the phase of the triplet potential. And so what's shown in this plot is if you take, in this case, this is potassium-39. It's in the low hyperfine state of the potassium-39. And if you take two of these potassium-39 atoms and you allow them to collide together and you look at what are the possible scattering lengths that are available if you vary the singlet and triplet potentials or the singlet and triplet phases, this is what you get. This is basically a plot of the scattering length of those two colliding 1, 1, F equal 1, MF equal -1 or +1 atoms as zero filled together in potassium-39. Thing is, of course, if you lay sodium on top of it in these scaled coordinates, it looks just like it. Cesium, it warps a little more, but you know, it looks just like it. Now, there's no reason to be surprised by, because in the end, there are, effectively, if you look at that problem, there are two singlets and a triplet. And you know, it's really nice that the physics works correctly here, because if you look at the scaled triplet, which goes from -infinity to +infinity, as you come across here, the scattering length goes through 2 pi. It goes through 2 pi because the triplet's in there twice. Whereas if you cut across that way, it only goes through pi once, and that's just because there's only one singlet. So, you know, again, this is the essence of the problem. And the real essence is, unfortunately, from an ab initio thing, we don't know when we start out these problems what AS and AT are. And finding them out is where there's a lot of beautiful physics. And a lot of things, and the fact is the physics, depending on where an actual system ends up on, in potassium, the answer is that you're up here. In sodium, you're over here. In cesium, you're down in this corner. Actually, I think you're down in this corner here. And so in each system, you end up in a different place, and the systems then end up with very varying different enriched physics as a result of where you end up. But again, you can start from this simple picture and learn quite a bit. Now, I want to say a little something for, again, the non-experts. Here is a, quote, chemist view of Feshbach's. And I'm happy to note that, I went from chemistry and became a physicist, and I see half of Fano students are becoming chemists. Now, they're telling you that they're just studying molecules, but in reality, they're trying to become chemists. So here's a chemist's view. I have some molecular levels. These molecular levels have a magnetic moment. And because that magnetic moment may be different from that of the asymptotes, they can go through that threshold. And when they go through that threshold, I can get a signal. And of course, that's just Feshbach spectroscopy, or magnetic Feshbach spectroscopy. Now, why I want to show this is because although cesium wasn't the first one done, cesium actually has some beautiful Feshbach spectroscopy in it. And in fact, it really is that experimental work that was done by Vlad Bulatich and Steve Chu that allowed us to finally crack cesium. And the reason cesium was so difficult is, like I said, I ended up in the corner. Now, I'm not showing you the full plot in cesium, but again, you can see one of these Feshbach-type resonances in the cesium plane. You see some narrow lines here. These are D waves. The problem is I told you there was only two parameters, AS and AT. Well, if that was all there was, and you wanted it down in that corner, life would have been easy in cesium, and Baudouin Berhard would have probably gotten the problem right a long time ago. But you got down to that corner. And the problem is if you look at this, and again, this is just a piece of that scaled triplet now. Again, this is minus infinity. It's not going very far. And this is plus infinity. As you go across one, it goes back to minus infinity. I just shifted it slightly because it's a little better. And so here again is this plot. The problem is this whole plot, if you start varying C6, just shifts down on the scale. All the features shift because it's the energy dependence that comes from the C6. And that C6, of course, as you can say, is a scaling parameter. We know what the mass is. It's the mass and the C6 that go into it. But we don't know what C6 was exactly. Get the wrong C6, you get the wrong answer in cesium. Then again, there's one more little piece of essence. And this one other piece of essence is the second order spin orbit interaction, which acts as a dipole-dipole interaction. And you can say it's not. It's nothing important, except that it changes how far the D waves are from this big feature here. It became another clue. And as we started out working with Vlad and Bulatich, when they started giving us the data, and we started looking at it, we became aware that, they had the answer to everything, because it should be possible, if you can fit all this stuff, to actually extract the cesium scattering links. Hey, we fit it all. And after we'd fit it, and we'd spent tens of thousands of CPU hours trying to understand everything, get everything to work, and it all fit well, we came back and we said, sorry, we can't give you the scattering links. And so you ask, what is the problem? Well, the problem was that ASAT, C6, and the second order spin orbit. And I can fit the spectrum with any three of those parameters. Didn't matter which three. You give me three of them, I could fit it. And the fourth one was free. So I still had a degree of freedom left in the problem. And so we were talking on the phone one day, and he said, what do we need to do? And I said, you need to find me a pure triplet resonance. And I would suggest where it is. We'll go calculate where we think it could be, depending on what the triplet interaction is. If you can tell me that, I can constrain all four parameters. So we started doing the calculations. 2 days later, they sent us the data. We were still doing the calculations. And in fact, it was a couple more weeks before we had enough of the calculations done that we could pin down the number. But again, we were able to very tightly constrain the numbers. And again, this is a lot of beautiful Feshbach spectroscopy. And again, if you understand the essence of the physics and what you can extract from it, you soon can then go back and do an MQDT type analysis and understand everything from a simple picture. But you had to get to the right place in phase space first. You had to find it. And it was the data that provided the parameters. I won't talk about this. This is just some bound states. There's some G waves. They haven't been published, but there are some other narrow resonances. So the only reason I put this up there is G waves. Look, in the Vlad experiments, they were basically at a few microkelvin. A few microkelvin, everybody would say it's S waves, and S waves only. They see D waves. They see G waves. And in fact, initially, they said they thought they might have seen something that everybody wanted them to see, which was these Efimov states, except that unfortunately we assigned all their Efimov states to G waves. Two-body physics all over again. Again, the thing is we do have the ability to actually reproduce the data, and it's very beautiful data. And what I should say, we have published these numbers on cesium. These are actually the most recent numbers. It's been done, work that's been done for almost a year and a half. We still haven't gotten the paper written. We're working on it. I know that the French group from PA, and they've been a big controversy for a long time. They disagreed with our numbers. I know that they now have numbers out. Their numbers are now in agreement with ours. They do overlap our most recent numbers. I would still tell you that I believe these are the most accurate numbers on cesium that exist, and that if you want to know what to use, I would use these numbers. What's going on at NIST? And so I spent years doing code collisions. Paul Julian pulled me in, dragged me into this field, and we converted Paul Lett into becoming a real collisions person, and wrote numerous papers. Well, when I came back to NIST and we started working, I became very interested in actually using these collisions, using the coherent nature of the collisions to do quantum information processing. So I want to go down that line for a few minutes, and I want to talk about some different kind of physics. But and so what I want to talk about first is I want to talk about the Mott-Insulator transition. And this is work that was done with well, basically, it was an idea that Peter Zoller basically came up with. And a lot of the Mott-Insulator transition work was done by Dieter Jakisch, but now I'm going to show you how to create a molecular condensate. And this is stuff that Vanessa Venturi, one of my postdocs, did as part of this interaction. And so what we want to do is we want to start off with a BEC that we're going to load into an optical lattice. And, of course, initially you have a superfluid or a long-range off-diagonal order or a Bose condensate. And we want to then raise the lattice to the point into where we get to a Mott-Insulator transition. And when we do that, once we get the Mott-Insulator transition, we're going to turn those atoms into molecules. And so the advantage is we have control of the system because we have laser parameters that will allow us to go between the two states. Now, Peter had mentioned, again with Dieter Jakisch, had basically 3 or 4 years earlier talked about doing this with the atom. So I mean, this idea of the Mott-Insulator was something that was pre-proposed. This is actually the experimental data of the first observation of the Mott-Insulator transition from the Emanuel Bloch and Ted Hansch in Munich. What you see here is as a function of lattice depth, they basically have these atoms in a condensate. There's initially no lattice, so if you just look at it, of course, you got a single condensate. You begin to turn on the lattice, and if you then instantly drop it, let it do an expansion, you get a diffraction pattern, which is effectively just the Fourier components of the condensate in the lattice. And you can see this happens. As you turn up the lattice, you can begin to see a few more Fourier components. All of a sudden, you turn it up far enough, and it's gone. Now some might say, oh, well, there may be something wrong here because maybe some noise in the system. But of course, they can turn it up to that point, and if they turn it up to that point and then turn it back down, voila, the Fourier pattern comes back. So something remarkable happens at a specific point, and that is basically the Mott-Insulator transition, where you go from having a coherent state to having individual atoms in localized wells of the system, a quantum phase transition. So we went about modeling this, and in part of it, we did this because we decided we wanted to make a molecular condensate, and I'm going to describe this process, and we're going to go through the physics a little bit. Again, in this language, there's a hopping term that allows you to describe atoms going from one side in the lattice to another side, and an interaction term for having multiple atoms on the same side. And this is the simplest thing. We're going to take realistic parameters for this. These are basically the parameters that are appropriate to rubidium-87. And you will see that there are 2 parameters in the system, J and U. And what we want to do is we really want to look at the change in J between J and U. If you have a very shallow lattice, of course the atoms are free to move, and so J is very, very large, and effectively the on-site interaction is small because the mean field is spread out. If I keep turning up the lattice, I can effectively make J go to 0, while at the same time I'm also slightly increasing U because I'm confining the atoms more and more. But effectively I can change the ratio of J to U. So that's my control parameter. It's just the lattice depth. And so if you do this and you do things in certain units, you can get a regime where you basically are dominated by J in a very shallow lattice. If you go to a large lattice, you can see that you're dominated by U, and effectively at a value of J over U equal to about 6 times the number of of lattice pairs, you have a sudden transition where your atoms become localized. So what is the idea of doing this engineering? We want to take a BEC, which everybody can perform today, load it into a lattice, raise the lattice up, get to this Mott-Insulator transition. And what we're going to do is we're going to take this, basically this superfluid that's in this lattice, and we're going to go to this Mott-Insulator transition, get it to where we have a well-defined number of atoms in each lattice, say 2. The benefit is if you have 2 atoms in a lattice is we know how to do a coherent process of converting 2 atoms that are really a molecule in a trap. I mean, it's not trapped by molecular forces. It's trapped by the potential holding the atoms. But do a Raman transition. And I can form a real molecule. And we will make the molecules yellow. Maybe they should have been dumbbells. And now I just undo it. I just unfreeze it. And I should be able to form a molecular condensate or a molecular superfluid. So here again is the Bose Hubbard picture. Here's a molecular picture. If I have 2 atoms in the trap, what I want to do, what I really have is 2 atoms in this in the relative coordinate in the highest level of the trap, because they are trapped now by the trapping potential, not by the actual molecular potential, which is down here. And then the object is, of course, to convert it from here into the lowest, most stable state of the system. So a little bit about the physics of what I'm going to show you. Again, we can go back to the Hamiltonian here. If you have n atoms and m lattice sites, it says I'm fully charged. Everybody who knows me knows I'm always charged. And I don't even need coffee to do that. Anyway, so if I have n atoms and m, I can work on this problem. And as long as J is much greater than U, it doesn't matter whether it's commensurate or incommensurate. I have a superfluid, and effectively, you will are in the BEC, you're in basically the Q equals 0 quasi-momentum state of the atom in the lattice, in the shallow lattice. Whereas when you go to the Mott phase, what happens is instead of having a superfluid, is you have a well-defined number of atoms in there if you're commensurate. If you're incommensurate, then you have a Mott core with a superfluid piece on top of it. So, I mean, there are the issues about extra atoms, and you're never going to be exactly commensurate when you do this experiment, so there's always going to be some superfluid component. And in fact, you actually find that doing the theory or doing the modeling from a theoretical perspective and putting on a computer, you have to kind of seed the break of the Mott-Insulator transition if you were actually in the commensurate case, because otherwise it just doesn't really want to go. But that's a numerical problem that can be handled. So again, we'll come back. There is one other detail in the experiment, is that not only is there the J and U, but there's an energy offset, because typically my Bose condensate is sitting in this magnetic trap, and so from one side to another, there's a slight offset that depends on where you are in the trap. And we put that in as well. Okay, so let me show you a few pictures. So here is basically a 2D picture showing the system when I'm in the superfluid phase. And what's plotted is basically the average number of atoms per well site, the variation in that average number, and the phase. And this is basically a 5x5 lattice with 25 atoms in it with this offset potential. So you can see that there's no atoms in the corner because the potential is highest in that diagonal piece, just by the way the trap is done. It's in the square lattice. So equal contours would be a circle, of course. And you can see there, nothing surprising. I mean, the density looks exactly like you want. And this is for a lattice depth of 3. Change it to 12. The number of atoms looks to be about 1. The variation in the number of atoms, you can't see this basically here, and I'm sorry. You can see on the very outer ring there is a small slight variation. If you look really, really hard at it, trust me, it's there. I mean, you know, it's amazing how well it looks on my screen, but you know, PowerPoint just doesn't always do what you want. When you look at the phase, it looks like it's gone, and that's good because it's what we actually wanted. So this works. What I'm going to do here is I actually want to show you the density matrix. So I'm going to just take 5 atoms in an array, but I'm now going to actually plot the fluid density matrix, rho ij, so we can look at the off-diagonal coherence. And of course, I'm going to start again in the low thing. I'm going to run a movie in a minute. So along the diagonal is basically the population in the whales, and the coherences are on the off diagonals. I'm going to do two different things. For 5 atoms and 5 whales, I can do an exact calculation. You know, when you start looking at the number of configurations, when you get up to realistic numbers, there's no way of doing the exact, so you need to make some approximation. What we did is we made a Gutzweiler ansatz. And so I'm going to run you and show you the difference between them. Here we go. We will start running the calculation. I'm going to stop it halfway down the way. There, we're going to stop it right there. And you can see that get the potential up to 17. It's diagonal. All the coherence is gone. Now, there are some annoying little attributes here. I mean, if you look at the exact calculation, you see that what residual coherence there is between adjacent sites, which is exactly what you get from a Wannier analysis or anything else. When you look at the Gutzweiler, you find that the coherence is between the two things that are out the farthest in the trap with the offset. And I can basically understand why it is that way, but I don't understand why the Gutzweiler gives it that way. I mean, in the end, it is because those are the two that are most have the biggest J's between them, but they're also the ones that are farthest apart. So there's clearly some problems with using the Gutzweiler ansatz.
Sorry, Carl. What is the Gutzweiler ansatz?
The Gutzweiler ansatz is I basically take an assumption that the wave function I start out with my trial wave function is an expansion in number states within each lattice site, and then a product of those expansions over each lattice site. And then I can either project it into a well-defined number or do the on number projected. So it's basically assuming a localized wave function that is expandable in terms of numbers. Now, again, you know, the thing is you get the phase transition here, but there are really no quantum fluctuations. I mean, this is just a wave function ansatz. And of course, if you run it back down, remarkably, the coherence comes back. It's always amazing that the models work. And I didn't even have to run it backwards. I just kept going in the same direction. Now the last piece. What's the molecular physics in the problem? You get the atoms together, and the problem is to get them down to the ground state and finding the pathway to do that. And so what you want to find is that the hardest path is the first step. But I mean, there is a Frank-Condon path down to the ground state. And what this shows is basically the Frank-Condon factors. These are 2 photon Raman Frank-Condon factors. And so to give you a view of what's actually happening in this situation is to show you here. You start with your free atoms. You absorb here up to some quasi-bound state. You come in, you come down to a level, you come over, you come back up, you come in, you come back down. And that's what was shown in that previous picture, because you're effectively absorbing at the outer turning point, emitting at the inner turning point in the Raman process. It's resonant, off-resonant Raman process. Now, there are some problems, because you can try to do this adiabatically, and you say, well, you know, I do the counterintuitive pulse sequence and just flop it over there very quickly. But it would never work. And the reason it would never work is because, unfortunately, if you try to put on omega-2 first and put it on strong so you can actually do that counterintuitive process and do the adiabatic thing, you find that you can actually create hot atoms. And in fact, what you will do is create hot atoms. And so when you look at all the timescales, the only way of doing this is effectively via a Raman process. And that means it's slow. But you can get the numbers to go, and you can do the conversion. And in fact, we estimate that the conversion can be done ideally at about 98 or 99% efficiency. So with that, I will skip over this next part because I know time is moving on. And I want to go to one other thing, and so we'll ignore the gates for a moment. And talk a little bit about lattice quantum computing. Now, one of the other problems that I became to be interested in is I have a quantum computer, and I have all these atoms in a nice lattice site, and I can do this because I can, again, do the Mott-Insulator transition. And one of the problems that you have is that, unfortunately, in this situation, I can interact atoms next to each other quite easily. And that's wonderful, because that means if I want to interact 2 atoms, 2 qubits, one over here and one over here, qubit A and B, then in principle, to do that, I need to swap the atoms all the way over. And of course, while I'm doing all these swaps over, which I can do, but errors will occur, and of course, I will screw myself up royally. So the question is how do I build a scalable architecture, quantum architecture, out of a system and where I only have nearest neighbor interactions? And in a lot of the quantum systems, this is exactly the case. So the idea came up as, how am I going to do this? And surprisingly, there's a way of doing it. And the way you do it is you come up with an architecture in which you have some qubits that are memory, shown by the qubits that are in the yellow boxes. And I have a quantum bus. All my others I will use as a resource. And why do I want to do this? Well, it became obvious that the reason you wanted to do this was because then I could do something else. And, well, actually you can do several things. One of the things you can do is you can create your bus however wide you want it. I can have it single channel wide, I can have it double channel wide. And so you can create your bus however you want it. And what I want to do is let me just skip this graph for a minute because I know time's running out. I'm going to come back down to what you want to do. The way I want to use the bus is I want to create an entanglement chain between the two distant sites I want to interact. And the way you do this is in a single set of interactions, I can interact neighboring qubits like this. Do this all in parallel, all at once. Two atoms.
Can you say what is your qubit in this case?
This is basically just the hyperfine state of an alkali atom.
And what is the interaction between them?
It could be the Rydberg gate, it could be the Motional gate. There's a whole number of gates that have been done. Any of the neutral atom gates will work, in principle. I mean, all of them will be trapped, and you can implement any of the gates. I think actually the Rydberg gate is the best gate, but that's a personal opinion, and it's another whole discussion of why I think it's best. Even though I have another gate that I myself did, and I don't even think my gate's the best. I think the Rydberg gate is the best. So you do the pairwise interactions. And then in the next step, what you do is you do a set of Bell stick measurements, which you do by effectively doing a control knot and a Hadamard. So in the next thing, I do that. What comes out of this? Well, what comes out of this is effectively that I now have this atom and this atom entangled. And surprisingly, these pairs are also entangled. And so in the next step, I can do that, and I can end up with two entangled pairs that are now here and here. Well, in reality, these are still entangled, but I have two long entanglement chains. Now, I want two long entanglement chains basically because if I'm using a decoherence-free subspace, I'm going to need them. But also, if I'd like to distill my entanglement because my measurements and my operations want perfect, I need them. But again, I can do this extraordinarily efficiently. And in fact, I can swap those last two to make my two chains look like that. And why would I want my two chains to look like that? Because my computer is made up of decoherence-free subspaces. And somebody can ask me the free question what a decoherence-free subspace is. Then each real qubit in my system, each logical qubit in my system, is two atomic qubits. And I'm going to want to do parallel operations on them in order to do my gate operations and to make this scale. And so I can very quickly create a situation where I have two entangled pairs there. And once I have those two entangled pairs there, I would do a set of controlled knot operations and I would teleport my gate. That is I never move the information. I will run my computer by using these resources to create teleportation and very long entanglement chains to actually teleport the gates across wherever I need to, and I can actually do this, and I can make it scalable. I can put the errors into the system and show that at least with this teleportation scheme that it seems to scale and will allow you to do the operations that you could not do when you were restricted to nearest neighbor interactions. Now, with that, I really should move to really the last slide, and I will do it this way because it's just the next one. But unfortunately, the reason is there was a lot of animation in that, and I don't want to go into that picture. But let me say a few things again in summing up about what I learned from the Fano. I mean, one of the things I learned from Fano was always ask, what is the essence of the problem? What is the essence of the questions? And in the end, this has really been something that's been useful in me tackling problems. He provided a bunch of tools for the code collisions. And I think he was right when he said, you know, these code collisions are kind of interesting because I myself see that this remains a playground for physicists because we have the control and we can get into all kinds of different situations where different interactions are the essence of the problem. And so I think this is great. And it is really essential to know the essence of the problem. And the final thing is you know, I believe Fano initially would have looked at quantum information and said quantum information is, because, you know, sometimes it took him a long time thinking about a problem before he actually realized that there was something to it. I actually think quantum information is something that he would eventually come around to have liked, because it will provide us a new way of thinking about extraordinarily complex quantum systems in which we have absolute control over the ability to manipulate them. Doing Shor's algorithm isn't what's going to be interesting. What's going to be interesting is that we're going to create quantum systems and be able to control and manipulate them, and the new physics that will come out and the new things that we can do are things that most of us don't have any clue as yet to what's going on. And with that, I would say thank you.